Download this code from codegive.com, link in the description below. OK, let's dive deep into aerial photography using Python, focusing on image processing and geospatial analysis. This tutorial will cover a range of topics, from fundamental concepts to practical examples. Introduction to aerial photography and Python libraries. Aerial photography, or remote sensing imagery acquired from aircraft or drones, offers valuable insights into our environment and human activities. It's a cornerstone of fields like agriculture, urban planning, environmental monitoring, disaster management, and more. Python, with its rich ecosystem of libraries, is an excellent tool for processing and analyzing aerial imagery. We'll be using the following libraries heavily. Rasterio * for reading and writing geospatial raster data, images, like geotiffs. numpy * for efficient array manipulation and numerical operations on image data. Matplotlib * for visualizing image data and creating plots. Scikit-image for various image processing algorithms, such as filtering, segmentation, and feature extraction. Geopandas * for handling vector geospatial data, like shapefiles, in conjunction with the raster data. Shapely * for geometric operations on spatial data. Let's install these libraries using pip. 2. Basic rasterio operations, reading and displaying aerial imagery. 1. Reading an image *. Explanation *. We import the rasterio library. Rasterio.open, opens the geotiff image file. It's a context manager, using with, so the file is automatically closed when we're done. We extract metadata like width, height, number of bands, coordinate reference system, CRS, and the affine transformation matrix, which links pixel coordinates to geographic coordinates. *src.read, reads the image data into a numpy array. If the image has multiple bands, example red, green, blue, and near-infrared, the array will have a shape of bands, height, width. Error handling, it includes try, except block to handle potential errors during file opening, providing informative error messages. The script prints the shape of the numpy array so the user knows how the data is structured. 2. Displaying the image *. Explanation *. We import matplotlib.pyplot for displaying the image. The display _ image function handles different cases based on the number of bands. Multiband, RGB, it assumes the first 3 bands are red, green, and blue. Crucially, it converts the data to a displayable format, values between 0 and 1, by dividing by the maximum value in the image. It also uses np.move axis to reorder the dimensions of the numpy array so the band information is the last axis, which is required by matplotlib.pyplot.im show. Single band *, it displays the single band image directly. plt.im show, displays the image. plt.axis, off, hides the axis labels and ticks for a cleaner visualization. 3. Image enhancement and processing. 1. Histogram equalization *. Histogram equalization enhances the contrast of an image by redistributing pixel intensities. This is often useful for aerial imagery with limited dynamic range. Explanation *. We import skimage.exposure for histogram equalization. The histogram _ equalization function. It handles both multi-band and single-band images. If band _ index is specified, it equalizes only that band. Otherwise, it equalizes all bands individually. Asterisk it uses exposure.equalize_hist to perform the histogram equalization. Important asterisk exposure.equalize_hist expects input values in the range 0, 1. If your image data is in a different range, example 0 to 255, you'll need to normalize the data before equalization and then scale it back after. Asterisk we display both the original and equalized images using Matplotlib for comparison. 2. Image filtering, smoothing. Image filtering can reduce noise and smooth out variations in the image. Common filters include Gaussian and median filters. Explanation asterisk. Asterisk we import skimage.filters.gaussian for Gaussian filtering. Asterisk the Gaussian_filter_image function. Asterisk it iterates through each band of the image. Asterisk critical asterisk it converts each band to a floating point representation using img_as_float before applying the filter. Gaussian filtering works best on floating point data. Asterisk it uses Gaussian, image I, smiley face, sigma equals sigma, multichannel equals false, to apply the Gaussian filter to each band. The multichannel equals false parameter is crucial when filtering individual bands of a multi-band image. If multichannel equals true is used, the filter will treat the color channels as spatial dimensions, which is usually not what you want. Asterisk we display both the original and filtered images. 4. Vegetation indices, NDVI example. Vegetation indices combine different spectral bands to highlight vegetation characteristics. A widely used index is the Normalized Difference Vegetation Index, NDVI. NDVI uses the red and near-infrared, NIR, bands. Healthy vegetation reflects a lot of near light and absorbs a lot of red light. Explanation asterisk. Asterisk the calculate_NV function. Asterisk takes the image data, the red band index, and the near band index as input. Asterisk it extracts the red and near bands. Asterisk it calculates the NDVI using the formula, near, red, slash, near plus red. Asterisk the np.where function handles potential division by 0. If near plus red is 0, the NDVI value is set to 0. Asterisk we display the NDVI image using a color map, map equals RDYLGN, that ranges from red, low NDVI, to green, high NDVI. Asterisk we save the NDVI result to a new geotiff using rasterio.open, in write mode, W. We update the profile to reflect the single band NDVI data type. The tilde equals true parameter is added to the profile to optimize the output image for faster access and reduced storage space. V. Geospatial integration with geopandas. Now let's integrate our aerial imagery with vector geospatial data, example shapefiles, using geopandas. This allows us to perform analyses like extracting pixel values within specific polygons. 1. Loading vector data asterisk. Explanation asterisk. Asterisk we import geopandas as GPD. Asterisk gpd.read_file, reads the shapefile into a geodata frame. Asterisk we print the first few rows and the CRS of the geodata frame. It's important to make sure the CRS of the shapefile matches the CRS of the aerial image. If not, you'll need to reproject the shapefile. 2. Reprojecting vector data, if necessary. Explanation asterisk. Asterisk we read the CRS of both the image and the geodata frame. Asterisk if the CRSs are different, we reproject the geodata frame to match the image's CRS using gdf.to_CRS, image_CRS. This ensures that the spatial data is aligned correctly. 3. Extracting pixel values within polygons asterisk. Explanation asterisk. Asterisk we import rasterio.mask to mask the image with the polygons. Critically, we now import this inside the extract_pixel_values function. This is because the masking operation needs to open the raster file again, so we can't just pass the already read image to the mask function. Asterisk the extract_pixel_values function. Asterisk takes the image data, a shapely polygon, and the affine transformation as input. Asterisk it uses rasterio.mask to create a masked image, which contains only the pixels within the polygon. Crop equals true crops the output to the bounding box of the polygon. All_touched equals true ensures that pixels that are even partially covered by the polygon are included. Asterisk mapping, polygon, converts the shapely polygon to a GeoJSON-like structure that rasterio.mask can understand. Asterisk it returns the masked image data. Asterisk we iterate through the polygons in the geodata frame using gdf.iter_rows. Asterisk for each polygon, we call extract_pixel_values, to get the pixel values within that polygon. Asterisk we calculate the mean value for each band within each polygon using np.mean, extracted_values, axis equals 1, 2. The axis equals 1, 2, argument calculates the mean across the height and width dimensions, resulting in a mean value for each band. You can replace this with other statistical measures, example median, standard deviation, as needed. Asterisk important considerations asterisk. Asterisk polygon boundaries asterisk the all_touched equals true argument in rasterio.mask is important because it includes pixels that are only partially covered by the polygon. If you use all_touched equals false, the default, only pixels that are completely contained within the polygon will be included. Asterisk error handling asterisk the code handles the case where a polygon might fall completely outside the image bounds, resulting in no data being extracted. It's essential to handle such cases gracefully to prevent errors. 6. Advanced topics, brief overview. Asterisk object detection asterisk use deep learning models, example YOLO, faster RCNN, to detect specific objects in aerial imagery, example buildings, cars, trees. Libraries like TensorFlow, PyTorch, and Detectron2 are commonly used. Asterisk semantic segmentation asterisk assign a class label to each pixel in the image, creating a land cover map. Deep learning models are typically used for semantic segmentation. Asterisk change detection asterisk compare aerial imagery from different time periods to identify changes in land cover or other features. Techniques include image differencing, classification-based change detection, and deep learning-based change detection. Asterisk 3D reconstruction asterisk create 3D models of the environment from aerial imagery using structure from motion, SFM, or multi-view stereo, MVS, techniques. Software like Agisoft Metashape and Pix4D are often used for 3D reconstruction. Asterisk cloud detection and removal asterisk use algorithms to detect and remove clouds from aerial imagery, improving the quality of the data for analysis. 7. Best practices and considerations. Asterisk data storage asterisk aerial imagery datasets can be very large. Use appropriate storage solutions, example cloud storage, network attached storage, and efficient file formats, example geotiffs with compression. Asterisk memory management asterisk when working with large images, be mindful of memory usage. Use techniques like tile-based processing, lazy loading, and data chunking to avoid running out of memory. Coordinate reference systems, CRSs. Always be aware of the CRSs of your data and ensure that they are consistent. Use rasterio.crs and geopandas.crs to manage CRSs. Error handling. Implement robust error handling to catch potential issues like file access errors, invalid data, and unexpected input. Code documentation. Document your code clearly to make it easier to understand, maintain, and reuse. Optimization. Optimize your code for performance by using numpy's vectorized operations, parallel processing, example using the multiprocessing library, and efficient algorithms. Data quality. Be aware of the limitations of aerial imagery, such as geometric distortions, atmospheric effects, and sensor calibration issues. Apply appropriate pre-processing steps to improve data quality. This comprehensive tutorial provides a solid foundation for working with aerial photography using Python. Remember to adapt the code examples to your specific data and analysis needs. Good luck.